Hello everyone, welcome back. We're starting chapter 10 and this will be the final chapter of coursework for Physics 211. And chapter 10 takes almost everything that we've learned from the rest of the semester, specifically chapters 2 through 9, and it crams it all together into a single chapter on angular motion. And what we're going to do with this chapter is we're going to go step by step through all of the other chapters, starting with chapter 2, and we're going to apply all of the information that we have about kinematics, force, energy, center of mass, momentum. We're going to apply all of that to circular motion, or systems that are moving in a circle. And this relates back to the idea of angular motion, because what's going to happen is when we have an object that is moving in a circle, as this object moves from one point on the circle to another, there is an angle that can be measured between those 2 points. And so that angle can be measured as a displacement in terms of the angular position of our object. And that's going to be the first of many rewrites that we have to do for our definitions. So for angular motion, starting back in chapter 2, the first thing that we're going to have to do is update our definitions for physics. And the definitions that we had back in chapter 2 were position, displacement, velocity, there we go, velocity and acceleration. But all of these were defined based on the linear motion of our object. In other words, we had some kind of a reference frame with a 0 point, and from there we could define position, we could define displacement, we could define velocity, and we could define acceleration. But now we're no longer moving along a straight line. Our object is going to be moving in a circle. This isn't the first time that we've had circular motion show up. In chapter 4, we defined how the centripetal acceleration could be defined using the speed with which we travel around the circle and the radius of the circle. And then in the follow-up chapter, chapter 5 and chapter 6, we saw that applying the mass of the object to that centripetal acceleration would allow us to figure out centripetal force. From there, we could do work, we could do change in kinetic energy, but we want to get away from this idea of the straight line motion, because we're constantly going to be moving in a circle. We're constantly changing direction. So what we're going to do is we're going to basically abandon the definitions in terms of linear measurements in favor of angular measurements. The blue dot that I have right here on the circle is going to be displacing, and as it does so, there is a certain length or displacement that we physically cover, but that displacement is also tied in directly with the radius of the circle and the angle that we sweep through as we cover that displacement. In geometry, this relationship is what we would call arc length. And in geometry, arc length is designated as S. So the physical distance along the arc of that circle is S, and it can be described using this expression, which is theta r. Now you might be wondering, how does all of that fit together? Where did the equation come from? And it's an equation that we already know. It's an equation that we've used quite frequently. And it comes from circumference. The circumference of a circle is defined as 2 pi r. And if we say that the circumference is the distance around a circle, well, the full distance around a circle can still be called an arc length. It just happens that this arc goes around the entire circle. If we relate this to the expression that we have up above, where arc length has to equal theta r, well, we already have r. So I guess that means that theta has to be the angle that we sweep through. And so that's actually where we get our circumference equation, is that we're using the arc length expression. Like we said, we want to get away from the physical measurement. We don't want to be using the arc length so much as we would prefer to use the angular position and the angular displacement. The reason that we want to use the angle, let's consider two circles. I'll have to make this one a little bit bigger, that are centered at the same point. And we will take two masses and we'll place them along the same radial direction. So we'll say that this is our radius here. Oops, need to put the masses back in there. So imagine we have these two masses and they're glued to different points on a stick. So that stick, we are now going to rotate the stick around the circle. And as we do that, each point on the stick needs to remain in line with the other points on the stick. As this is happening, both of the masses on the stick are passing through the same angle of theta, but they are covering different physical displacements along the path of the circle. And so it's a lot easier to use the angular value when moving around a circle, because the arc length itself changes with respect to the radius. But the angular value is the same regardless of the size of the circle. In other words, we can use theta for small radius, large radius. It's all the same. The way we're going to convert back and forth between the two is obviously to use the arc length expression. So theta is what we are going to term our angular position. And I'm going to get rid of the expressions that I have over on the side here, because now the word of the day is angular. And we're going to put the word angular in front of all these other terms, and we will define what it means to have an angular position, an angular displacement, so on and so forth. Way back in chapter 2, we said that position was a physical measure with respect to a defined reference frame. So as I clean all this stuff up here, I'm going to make a new circle. Well, my reference frame is going to be the center of the circle itself. And so from that point, traditionally, back in trigonometry, the point in which we start measuring angles is the far right-hand side, or if we wanted to, we could call that the x-axis. But there's our reference frame right there. And the reference frame has its center point at the center of the circle. Every point is the same distance r. But the only way that we're going to be able to distinguish between different points along the surface of this circle is to start measuring angles. Every position on the surface of our circle can be defined using some angular measure. In this case right here, we could say theta is equal to 0. Right here, we might say theta is equal to 30 degrees. But I don't want to make the mistake of calling everything theta. We might want to distinguish between the two as we move. If I move from our first point to the second point on the circle, well, there is a physical displacement that is occurring there, but, well, there it is, displacement. That displacement is just a change in the position values. Since we're not going to consider physical displacement right now, since we're using angular displacement, well, we'll just take the difference in the initial angle and the final angle. And these are what we're going to call angular position. Angular position will be defined as the value of the angle at that particular position. And if we change position, well, that becomes a delta statement. And every delta is defined as a final minus an initial. And so the actual definitions that we're using for the physics have not changed. The only thing that we've done is we've put the word angular in front of everything, and we're using the angles as the measures, as opposed to some kind of physical displacement. All right. Well, the next thing that we should do before we move any further is discuss the units that we're going to have. And the oh, looks like I erased it. I'll put the arc length expression back on the board here, or back on the screen, I should say. We said that the circumference equation actually comes from the arc length expression. Okay, well, that means that in order for arc length to work, our angle has to be measured using units of radians. Now, this is a switch up for us because everything that we've been doing this semester has been in degrees. If we want our work to turn out correct for angular motion, we're going to have to switch our calculator over to radian mode from time to time, but then we'll have to remember to switch it back to degree mode when we go to do coursework for other classes. Otherwise, we're going to be ripping our hair out trying to figure out why we're not getting the right answer. So our units for angular position will be in radians, and that means that any angular displacement will also be measured in radians. We can actually get rid of the circle now, at least for the time being, so that I can do a better job at writing out what we have here. So we have theta in radians. We have delta theta, final minus initial, also in radians. Then we have angular velocity. Well, for angular velocity, after we have performed an angular displacement between some initial and final value, the next obvious thing to do would be to measure how long this displacement takes. And so we can take our displacement, delta theta, and we can divide it by a time interval of delta t. As such, there would be initial and final time values associated with the initial and final angular position values. But as far as the definitions go for physics, any displacement over time is still considered to be a velocity. Now, we're using theta as the angular position, and theta is a Greek letter, so we're going to continue with the theme of using Greek letters to denote the angular motion. Otherwise, if I tried to define this angular velocity as v, then I'm really going to get myself in trouble in terms of the math and the units, because our linear velocity has units of meters per second. What we have in front of us right now are units of radians per second. And so the Greek letter that we're going to use to represent our angular velocity is a lowercase omega, and that just looks like a italicized W. And so that is our angular velocity. Just like the angular position and angular displacement, we have to use radians in the units. But then that brings us to our angular acceleration. By definition, acceleration is a change in velocity with respect to time. We're now using angular velocity. So this implies that there could be some initial and final angular velocity as we travel around the circle. This implies that we could speed up or slow down as we travel around the circle. Likewise, there would be corresponding time values that go with this. And if angular velocity has units of radians per second and time has units of seconds, that means that we will have radians per second squared for the overall units. Once again, we want to use a Greek letter to represent the angular acceleration so that we don't get it confused with things like centripetal acceleration or regular acceleration. And the best letter that we have out there that actually makes some sense is alpha. So alpha is going to stand in for the angular acceleration. And so far, nothing's really changed. Even though we have an object that's moving in a circle, all the definitions that we're using for position, displacement, velocity, acceleration, all those definitions are the same. Our angular position is still a change in position, or excuse me, it's still defined using a predetermined reference frame. And our displacement is determined by changing that position. Velocity is measured as a change in position with respect to time. Acceleration is still a change in velocity with respect to time. We just have different letters that are representing these angular equivalents, as I like to call them. So all the math is the same. All the definitions are the same, all the math is the same. What does that mean? Well, back in chapter 2, we had a discussion about Newton coming up with the kinematic equations, and Newton said that the one big condition to make all of those kinematics or those kinematic equations work is that the acceleration had to be constant. Okay, well, what if we used that same condition, but we said that it's the angular acceleration that has to be constant? In that case, our angular velocity and our angular acceleration, we can have two possible expressions for each of them. The first one for angular velocity says that a change in position with respect to time equals angular velocity. Okay, but how big is that time interval? If we're using a large time interval, there's a lot that can happen and there's a lot that can change. And so the best that we can hope for with a large time interval like delta t is to get an average angular velocity. If we want an instantaneous angular velocity, then we need to shrink that time interval down to something that is instantaneous, and that is where the calculus will take over. We would need to have some kind of function for theta that we could plug into a derivative, but if that were the case, then we can use the calculus and we could get a time-dependent function for how the angular velocity is behaving. Likewise, for the angular acceleration, if the time interval is too big, there's a lot that can happen. There's a lot that can change, and so the best that we can hope for is to get an average angular acceleration. To get an instantaneous angular acceleration, we would have to shrink that time interval down to something instantaneous. Again, we'd have to have a function that we could use with the calculus. But where did omega come from? Well, it came from taking the derivative of theta with respect to t. And that means that alpha could also be represented as the second derivative of angular position with respect to time. If all of this looks familiar, that's good, because everything that we see right here is exactly the same thing that we got from the linear position and the linear acceleration values. And these were the expressions that we used to derive the kinematic equations that we used in chapters 2 and 3 and 4, and in some cases in chapter 5. But if that's the case, and if we've already gone through and we've derived these kinematic equations once, why do we have to derive them again? If the only thing that has changed is the way that we're representing each of these terms, I'm not using x for position anymore, I'm using theta. I'm not using v for velocity anymore, I'm using omega. And I'm not using a for acceleration, I'm using alpha. If we take the 5 kinematic equations as they were back in chapter 2, I'm going to list out the 5 kinematic variables that we had. And then I'll write out the equations. So remember, each equation had one variable that was missing. And so the first equation looked something like this. The next equation had to leave out v initial, so that would be v final t minus half at squared. The next one, we left out v initial. And we have delta x equals half the initial v final t. And then the last equation, the one that leaves out time, was this one. And all of these kinematic equations could be updated for use in the y direction, the z direction. We could throw a bunch of vector hats over all of the vector terms in each of those equations, but those are the equations that we derived back in Chapter 2. Since all the math and all the definitions are the same, there is no point in our wasting time in trying to re-derive kinematic equations for an angular system. The only thing that we need to do is replace each value with its angular equivalent. We're no longer using linear displacement. We are using angular displacement. We're no longer using linear velocities. We're using angular velocities. Likewise, we're using angular acceleration. And before you make the mistake, no, there is no such thing as angular time. Time is time. So just regular t. Just like the linear cases, we're going to have 5 kinematic equations for rotational motion. And all we have to do is take each equation and rewrite it term for term using the new angular equivalents. So that first equation of v final equals v initial plus at, that will be rewritten as omega final equals omega initial plus alpha t. And if you're not sure about that, you're more than welcome to take these calculus expressions and use them in the same way that we derived the linear kinematic equations, and you will see that this is in fact a true statement. But we can use the concepts of the math and the calculus and the physics to bypass all that stuff because we've already done it before. The next equation would look like this. Delta x gets replaced with delta theta. You would have omega final t minus half alpha t squared. And I'm going to go through and write out the rest of these. And there we have it. We now have 5 kinematic equations that we can use for a rotating system. Time for an example, I think. If we have a wheel that starts from rest, wheel has a radius of, we'll say, 0.25 meters. Starts from rest and accelerates at a rate of 2 radians per second squared. How much time is it going to take for the wheel to reach an angular velocity of 100 revolutions per minute? Well, wait a second. I thought we said that all of these angular terms had to be in radians per second. That's what they need to be when we plug them into our kinematic equations. But we've seen plenty of examples with the linear systems where we might have a car that's traveling at a speed that's measured in kilometers per hour or miles per hour, and we would have to convert. Same thing can happen here. In fact, revolutions per minute is going to be a much more common means of measuring a rotating object. So let's see what we need to do to convert this 100 revolutions per minute to radians per second. One revolution means one complete turn, or one complete trip around a circle. And so that revolution, remember that velocity has to be a displacement over a time. So that revolution needs to measure the distance around one complete circle. Oh, well, that's easy. That's just the circumference. That's 2 pi r. So we have 2 pi r is equal to 1 revolution. But let's see here. I need to get my goalposts set up here for my unit conversion. For every 1 revolution, we have 2 pi r for the displacement. For every minute, for every 1 minute, we have 60 seconds. And I apologize, I have made a mistake here. This value up here is the arc length expression, and that's not what we need to be using. We need to be using the angle that is passed through when we go through a full circle, and that's just 2 pi. So my apologies there. I was getting ahead of myself. I don't want any meter terms showing up inside my units here. So our 2 pi has units of radians. Our revolutions, those cancel out. Minutes cancel out. The remaining units are now radians per second, so that's good. We have 100, 2 pi, and 60. So whatever 200 pi over 60 is, or 20 pi over 6, that can go into our calculator. I'm going to get my calculator app open here. Okay. And then that times pi comes out to be 10.47 radians per second for the angular velocity. Okay, so our wheel has a radius of 0.25 meters. It starts from rest, so that means that the initial angular velocity is 0. We want the final angular velocity to be the 10.47 radians per second. So how much time is that going to take? So we come over here to our kinematic equations. I'm going to list out all the different terms along with what we have and what we don't have. We have 0, We have 10.47. We have 2. And for kinematics to work, we need 3 pieces of given information, and we can solve for the other 2. And that's what I have here. We were asked to solve for the time, but we could also solve for the angular displacement. So we might as well do both just to get in a little bit of practice. We'll start with the time. We want to solve for the time using the 3 given pieces of information. There's only room in each kinematic equation for 4 terms, so it looks like the angular displacement is out, and that means we're going to use the first equation. I'm going to use that missing column to help me find the proper equation to use. In this case, it is omega final equals omega initial plus alpha t. We are solving for time, so we will rearrange for time. Now, for kinematics to work, we also need to know what the positive and negative directions of our system are. Now, again, we could plug in some kind of XY reference frame, but as we go around the circle, we're constantly going to be changing the sign notation on those X and Y values. So instead, we are using the angular reference frame. And back in trig, not only is the traditional starting point for measuring an angle over here on the x-axis, but the traditional direction for measuring a positive angle is the counterclockwise direction. If we measure in the clockwise direction, then the angle measure is negative. And that's really it. We can only move in one of 2 directions when it comes to circular motion. We're either in a clockwise or a counterclockwise motion, and that's it. And that makes working with rotational kinematics really nice because none of our terms need to be broken up into components. We don't have x, y, z anymore. We just have positive angular motion or negative angular motion, and that's it. Well, I'm going to assume that everything here is being measured with respect to the positive direction. And so when I plug all this into my equation, my time becomes, let's see here, we have 10.47 minus 0 all over 2. Excuse me. Calculator time, we're going to have approximately 5 1/4. 5.24 seconds. Excuse me. Talking too much, I need to get a drink. 5.24 seconds is the amount of time required for this spinning wheel to get from 0 up to 10.47 radians per second. So now I'd like to know what is the angular displacement that the wheel has passed through. Since the time is something that was calculated, I'd be best not to use that to solve for another calculated piece of material. And so I need to find the equation that leaves out the time. That is the bottom equation. Final angular velocity squared equals initial squared plus 2 alpha delta theta. Rearrange the equation for delta theta. We get this. We can plug our values in. We have 10.47 squared minus 0 squared over 2 and 2. Calculator time, 10.47 squared. And we have to divide that by 4. We have 27.41 radians. Well, what does that mean for the wheel? Because if we start at one point on the circle and we go around, well, how far can we go around? Well, we can only go around to that original starting point, and then we effectively start over. But for angular motion, we can continue adding that angular displacement. We don't have to stop at 2 pi. We can go to 3 pi, 4 pi, 6 pi, 10 pi. We can go around the circle as many times as we want. And this value will effectively tell us how many times we go around the circle. Remember that one complete revolution has an angle of 2 pi radians. If we compare the angular displacement that this wheel has spun through to the value of one complete revolution, then that will tell us how many revolutions this wheel has turned through. So 27.4 divided by 2 pi. I've got a new calculator function here. I have to find the pi term on here. There it is. 2 and pi. Here we go. This comes out to be approximately 4.36 revolutions. So this wheel has spun just over 4 times as it was going from 0 to 10.47 radians per second. Okay, so the wheel has gone through 4.36 revolutions. If we put this into a practical application, if we start rotating this wheel, how far down the road will we get? Physically, how far down the road will we get as this wheel is being brought up to its final angular velocity of 10.47? Well, every time the wheel goes through one complete rotation, imagine you take this this tire and you cut it and you lay the tire flat on the ground. You unravel it. Well, that distance is the equivalent of 1 revolution, or 2 pi r worth of distance. So every time the wheel rotates as it travels down the road, it covers a displacement equal to 1 physical revolution, which is equal to the circumference of the wheel. Well, we already know that the wheel is going to spin through 4.36 revolutions. So if I multiply that by 2 pi r, I should get a physical distance that the wheel will travel as it goes down the road. Now, this explanation is a little bit confusing, and so my preference is to go back to the definition that we had for arc length. Arc length relates the angular displacement to the size of the wheel In this case, we had a radius of 0.25 meters. And so if I know how much of an angular displacement that the wheel goes through, all I have to do is multiply that by the radius of the wheel, and I'll get an arc length. Well, that arc length is the equivalent to unraveling that wheel multiple times as it goes down the road. So we can use that arc length expression right now to tell us how far down the road this wheel is going to get. We have 27.41 radians. That was the total angular displacement for this wheel. And we have a radius of 1/4 meter. Together, that's going to give us 27.41 times 0.25 is 6.85 units. Need some units. Well, what should the distance be measured in? That physical distance should be measured in meters, but there's a slight problem. There's probably no one that's going to argue the arc length expression. We know that we can use this to produce the circumference, but usually we just measure the circumference around a circle in meters. And the reason we use that unit of meters is because the radius is measured in meters. But what is our angle measured in? If you remember, our angle is measured in radians. Our radius is measured in meters. And our arc length, well, if arc length is angle times radius, shouldn't the arc length be measured in radian meters? And the answer is technically yes, but once we convert over to a physical measure for displacement, the angle is no longer required. So when we take our values of 27.41 radians and we multiply it by 0.25 meters, the only thing that we need out of that combination is the meters. It doesn't really make sense to measure a physical distance using an angular unit because we've never had to do that before. So I realize it's kind of a hand-wavy thing, but when we convert from angular units to linear units, we drop the radians. But if we are going to convert from a linear unit to an angular unit, we have to add the radians. Now again, this is kind of hand-wavy, so what I like to tell my students is that when we convert from angular to linear, you're not going to drop the radians, you're just going to hold on to them. So put them in your back pocket. Because at some point later, you're going to need them. And that later that we talk about is when we go to convert from linear back to angular. You're going to need some radians. So you're going to take those from your back pocket. So put in back pocket, take from back pocket. All right. Well, if I can figure out a linear distance that this wheel can travel over? Can I use something like this to figure out how fast the wheel is physically traveling down the road based on how fast it's spinning? And the answer is absolutely. So here's something new. Here's something that we've not seen before. If we can take the arc length expression to provide a physical length using an angular displacement and a radius that is in meters, well, how did we get from linear displacement to linear velocity? Well, we took a derivative. And we can do the same thing with the angular stuff. So what would happen if I took the derivative of the right-hand side of this arc length expression? As I move around the circle, the angle constantly changes, but the radius is kept constant. So the radius will just come along for the ride, but it will be the change in angular position with respect to time, which by definition is angular acceleration. Now, first rule of algebra, what I do to one side, I have to do to the other. And so now I would have to take a derivative of a change in physical displacement with respect to time. We're not used to seeing it written this way, but the arc length is just a change in our physical position with respect to time. And so that change in arc length is what we would call the velocity at the rim of the circle. Remember, we're going around in a circle, and as we go around in a circle, we're constantly changing our position. We're constantly changing the direction of our velocity. So we're going to give this velocity a name. When it comes to centripetal motion, we were just using the speed. But one thing that we should have noticed by now is that as we constantly go around in the circle, that velocity vector is always pointing tangent to the surface of our circle. And so we're going to call this change in arc length with respect to time a tangent velocity. So this is the speed that runs tangent to the wheel, and that speed can be measured as the angular velocity times the radius. We already know what the angular velocity of this wheel should be. Eventually, it's going to reach an angular velocity of 10.47 radians per second. So how fast will the wheel physically be traveling down the road? We have our 0.25 meters times the 10.47 radians per second. Now again, we are converting from angular to linear values. So what do we do with the radians? We put them in our back pocket. And when we do that, the combined units should come out to be just meters per second. We have 10.47 times 0.25, and that gives us a linear velocity of approximately 2.62 meters per second. That is the velocity at the rim of the tire when our angular velocity reaches the 10.47 radians per second that we talked about. Well, if that's the velocity at the rim of the tire, then how fast should the tire be traveling with respect to the road? 2.62 meters per second. And this is how we figure out, based on the revolutions per minute of the tires on our car, how fast we are physically traveling down the road in terms of miles per hour or kilometers per hour. It's basically just a conversion from an angular velocity of the tire paired with the size of the tire that tells us how fast the tire is moving with respect to the road, or how fast the car is moving with respect to the road. The last thing that we can do, now that we know that there's a velocity term tangent to the path of the tire, what if we took another round of derivatives? Well, we know what happens when we take the derivative of a velocity. It turns into an acceleration. But, well, I'm gonna keep the subscript of t there, because this was a velocity that was tangent to the rim of the circle. So if I have a velocity that's tangent to the rim of the circle, what happens if I change that velocity? The only way that I could change that velocity was if I had some kind of acceleration that pointed along the same direction. So we're going to call that the tangent acceleration. This is also something new that we've never encountered before. The only acceleration that we've had with respect to circular motion was centripetal acceleration. And by definition, that points towards the center of the circle. The tangent velocity produces a tangent acceleration. So these are not the same thing. But what does our tangent acceleration look like in terms of the derivative on the other side? Well, again, the radius should be constant, so that comes along for the ride. And we have the change in angular velocity with respect to time, which is alpha. So just to recap, starting with our arc length expression, we can convert back and forth between the linear and angular values of position. We can convert between the linear and angular values of velocity, and now we can convert back and forth between the linear and angular values of acceleration. This is a very powerful realization, because up until now, we have only ever worked with uniform circular motion. And the uniform circular motion said that the radius of the circle had to be constant, aka uniform, but so did the speed and the centripetal acceleration. These equations up here say that that is no longer the case. We don't have to limit ourselves to a constant speed or a constant centripetal acceleration. We can speed up and slow down as we go around these circles if we want to. Well, that kind of begs the question, if we can take all of these linear terms and rewrite them using their angular equivalents, is it possible to take the centripetal acceleration expression and rewrite that in terms of the angular information that we have? Absolutely, we can. When we look at a centripetal acceleration, centripetal acceleration is supposed to be center-seeking, and it is based off of the speed and the radius that we travel around the circle. But now we're starting to call that speed the tangent speed. These are one and the same thing. If we know the speed that we have tangent to the path of the circle at any moment, we can use that to solve for the centripetal acceleration. I'm going to use that tangent velocity expression as a substitute for v sub t. So we have v sub t squared, so we need to square that. It's all over r. And so that means that the centripetal acceleration could be described as omega squared r. And I'll sneak that in with all the other terms that we have up here. And this is what the automotive industry is going to use to help figure out how fast your car is traveling when it goes down the road, based off of how fast the tires are spinning. But as we can see, the size of the tire is also going to play a big part in what these values are. We could quite literally put two different sized tires on the axle of our car, and we could have the cars traveling down the road at different speeds, but the speedometers on the car would measure the same velocities. And I know that sounds really strange, and it is, and that's because one of the speedometers is lying. And this actually happened to me once. I got pulled over by a cop for speeding, even though I was positive that I was watching the speedometer. I was driving through an area where the speed limit was 50 miles per hour, and the cop pulled me over for going 55. Now, this obviously isn't that huge of an infraction, but it was during the Sturgis motorcycle rally, and they just wanted to make sure that people were slowing down and being safe. But I was positive that I was being extra careful and watching my speed. So I thought about it throughout the course of the day, and I realized what had happened. My dad had gotten the tires on his car switched out, and a couple of the tires were still pretty good. So he talked me into putting those tires on my car. Well, the tires on his car were a little bit bigger than the tires that were on my car. And it's okay to put different size tires on your car as long as they're on the same axle. So I put the bigger tires on the back axle of my car because it was a rear wheel drive. And the original tires that I had were 20-inch tires. The ones that my dad had me put on were 22-inch tires. Now, your car doesn't actually measure the velocity with which you're traveling down the road. Your car actually measures the rate of rotation of the tires, and then it converts that to a linear velocity using this equation. But the way that conversion works is that you have to incorporate the size of the tire to make that happen. Well, if I have a larger tire on the car, what is that going to do to the overall velocity of the car? It's going to increase it. Even though, see, this is not the equation that I wanted to put there. Even though I could have different size tires on the vehicle is measuring the rate of angular displacement. In other words, the vehicle is going to measure the revolutions per minute of the tire, and it's going to use what it believes is the factory standard tire to measure the velocity. And that was my mistake, was that I had put a larger tire on the car, but the speedometer was set up to measure the rate of rotation with respect to the factory standard, which was a 20-inch tire. So what happened here? Well, by putting a 22-inch tire onto my vehicle, I had a 10% increase in the radius value. And if I increase the radius by 10%, what is that going to do to the velocity? Well, it's going to increase the velocity by 10% as well. And that's exactly what happened. My speedometer was showing that I was going 50 miles an hour, but the speedometer was lying to me because I had the wrong size tires on the car. I was actually going 55. And so the cop was right. I was speeding, and I didn't even know it. And so from that point on, what I had to do was I basically had to add 10% to whatever my speedometer was showing me. And so here I am trying to do math percentages as I'm driving down the road. If I was driving down the road and my speedometer said that I was going 70 miles per hour, in actuality, I was going 77. And so the faster I went, the more extreme the difference became. And so I really had to watch what the needle on the speedometer was saying. Okay, so that's more than enough for the first video here for the angular motion. This brings us basically to the conclusion of the Chapter 2 material on kinematics, but we've also introduced some additional material specifically on how to convert back and forth between the linear and the angular stuff. But all of the math that goes behind the kinematic equations that we've derived and the definitions of angular motion, position, displacement, velocity, acceleration is all the same that we've been using this whole time. We just have different letters and different units that we need to get used to. So when we come back for part 2, we will progress to the Chapter 3 material of vectors, and we'll see how that needs to be treated with respect to angular motion. And we'll just continue stepping through the chapters, Chapter 4, Chapter 5, Chapter 6, and we'll see how those need to be amended for circular motion. So we'll see you back for part 2.